Good afternoon and welcome to another lecture in MAE 113. My name is Richard Kohar and this is lecture 8, the formal definition of the derivative, covering section 1.3 in our textbook, and differentiating polynomials, section 1.4. Perfect, that's good to hear. So we just finished quiz 2 and I will post assignment 3 tonight. Again, this will right after I get to do my lecture and I get to review some of the grades from today's quiz. So without further ado, let's start. Let's do an example, just kind of like a warm-up. So again, if y equals x to the fourth, then dy by dx is what? So eventually I will get to, I have to figure out, there's some sort of setting in the quizzes to allow the, see what your, what you got right and what you got wrong. And hopefully it just gave you the grade, at least for now. I'm not sure. I have to go back and read the manual a little bit closer. But I will do it. I will, yes. Okay. So hopefully that answers the questions. I have to find the setting for that to switch it on. And what I'm going to do right here now is I'm going to do the derivative of x to the fourth. And I need to recall what the definition of the derivative is. Delta x. As for Ty's question, he's asking why there was a half a mark, and some of the questions were just worth half a mark and others were worth 1 mark, and I think 1 or 2 questions were worth 2 marks. Okay, so now we need to substitute in the x plus delta x in for this. So this is my function. So it's got to be x plus delta x to the fourth minus x to the fourth, all divided by delta x. So hopefully I answered the questions there. So now I need to expand this out. And if I do answer the question, just give me some sort of confirmation if that's good enough, or I can expand on that. Okay. So when we expand that out, we're going to use the binomial expansion theorem. So again, I kind of write out my terms. I have 2 terms here, this one, and I write this one in descending, and then the other one, the delta x, in ascending order. Oops. Okay, I'll do this. And then I have a delta x squared, delta x cubed, plus I have a delta x to the fourth here. So I just copy down my coefficients here, 1, 4, 6, 4, and 1. Okay, so then that's what my expansion is going to be. So thank you for having to deal with learning by live stream. The reason is there's a delay. I think maybe about a 10, 15 second, maybe even 30-second delay. So I might not see instantly your question, and then I have to look up and read it. So the follies of technology. So, and of course, if you're don't feel comfortable putting a question in the chat, I would say make a note of the time and send me an email too, and that can also help me. Okay. So that can cancel because I have an x to the fourth and the minus x to the fourth. And then I can factor out the delta x's here. I have a delta and x in each term, so again that factors out. 4x cubed plus 6x squared delta x plus 4x delta x squared plus delta x cubed. Oh, yeah. And take your time. Well, I mean, on a test you have a certain amount of time, but when you're doing this at home, make sure that you're writing out the steps, because eventually you will have to show this on the test. At least you'll have to demonstrate, at least in one instance, where you're using the definition of the derivative to find what the answer is. And you'll have to show your full workings. Okay, so I mean, I can apply this limit now to each one of these by the sum rule. But if I apply it to here, this goes to 0, this goes to 0, this goes to 0, and this goes to 0. So I'm just left with 4x cubed. And that's our derivative. Okay, so part of intelligence is that we are able to abstract, and by doing abstraction, what that means is that we can find patterns. It'd be nice to be able to reduce some of the complexities. If, for instance, if we could find a model or a rule, and then we can simplify kind of having to do kind of this laborious work. So let's see if there's a pattern. So we had, for here, we had x squared. And this is from our previous lectures. So for this function, x squared, we found that the derivative, using our definition, was 2x. And similarly, we have x cubed. What we found was 3x squared. And just now, what we found here was x to the fourth. was 4x to the 3. So what we're noticing, we want to find what a pattern is. Whoops, not n. So if I have it for x to the n, which is where n is kind of a positive integer, or you can think of it as just a natural number, then what is the derivative of it? And we notice that for this one, we have 2, it drops down by 1 degree. We have 3 here, and it drops down by 1 degree, becomes 2. Again, 4 drops down 1 degree. So, same thing here. I have x to the n. Well, let's drop it down by 1 degree, so n minus 1. And we notice in each of these that x to the x squared, the 2 is in front. So it moved from as an exponent to in front as a coefficient. Same thing here. We have 3. It came down in front, and now it's a coefficient. Same thing here. The 4 came down, and now it's a coefficient. So what does that mean? It means that this n comes down in front and becomes a coefficient. Now this is our guess. Or in mathematics, we can have it as a proposition. So again, like from 106, we did proofs with propositions. So it's not good enough in math to just say that we see a pattern and this is our guess, that we've kind of had some inductive reasoning. We need to show that this is true using some deductive reasoning. So let's do 2. Move some papers out of the way. There we go. So this was our proposition. Let's put it here, yes. So if we have some function f of x, x to the n, then the derivative is n times x to the n minus 1. We can also express this using Leibniz notation. So equivalently, so in Leibniz notation, so we had an operator, so we have d by dx. So we're taking the derivative with respect to x of the function x to the n. We're saying that it's n times x to the n minus 1. So everyone fears this word proof, but really, we've been doing little proofs all along, showing, for instance, this is a very simple proof, which is y equals x to the 4th dy dx, that the derivative is 4x to the 3 using principles. Again, you can think of that as a proof. Now, what we want to do is we have this proposition which is a little bit more general. We'd like to show that it holds for lots of n's. So again, the nice thing about this is that once we've done this, at least in mathematics, that once we have shown it once and it's correct, that we shouldn't have to do the work again. So for this proof, we'll restrict this to the natural numbers so that the exponent there is a natural number. And the reason for that is we're going to be factoring. Okay, so we let f at x equals x to the n. Then using the definition of the derivative, we'll have and this is probably something that you'll have to memorize, but again, it's the difference of our y's divided by the difference in our x's. Now substituting in our function, it's x to the n, so it'll be x to the x plus delta x all to the n. And same thing, we have f of x, and so in this case, our f of x is just x to the n. Divided by delta x. Now this is the part that we need to factor. Because what we would like to do is get this factor out, kind of like get something like with a delta x so that we can cancel out the denominator. Because at the moment we can't substitute in the delta x in because our denominator is 0, which is forbidden. So we can't do that. So we need to do some algebraic manipulation. So what we're going to do is we recall our difference of squares. So remember when we had a squared minus b squared is equal to a plus b times a minus b. We also have a difference of cubes. So if I have an a minus b, let's say it's a squared plus ab plus b squared times a minus b. So you can kind of see that there's a pattern, there's a plus. So what we do then is that in general, that a to the n minus b to the n is equal to, so again it's just a n minus 1 plus a n minus 2, oops, plus. So the a's will be descending and the b's will be ascending in the exponent. So I have a minus 3 plus dot dot dot. Just give me a second while I write this out. So I have B0, B1, B2, and then I'll skip all the way. So I'm going from AN minus 1, AN minus 2, AN minus 3, all the way down to A, and then A0. So in this case, no, that's correct. And then at the end, I'm just left with A minus B. Now, to show that this is also true, a way of checking that is, just re-expanding everything out, collecting your terms, and simplifying, and you should get AN minus BN. So using this, what we're going to do is we let A equal the x plus delta x, that's our first term, and the b equal x. So if you want to think about it like this, there's my difference of squares, because there's my n and there's my n. Well, not difference of squares, but my difference of exponents here. So I have an a is here, and my b is here. So you can see that we can apply that formula. So doing that, what we can do then is now we can write out our difference, which was, it's going to be pretty big, so I'll write over here. So x plus delta x to the n minus, so there's our a, and here's our b, x to the n. So I'm going to write this one out in front here, so I have a minus b. So just to make sure that, I'll pick a color. Let's pick this one. So I'll just move this to the front here. So when I do my a minus b, it's a minus b. Okay. And then we expand this out using a square bracket. In this case, here's my a, so I have x plus delta x n minus 1 plus x plus delta x n minus 2 times b, which is x, plus dot dot dot. Let's skip those next terms and just work to the end here, so that I get, so it's a here, so x plus delta x times b, which is n minus 2, plus, and then the last one is just b, which is x, n minus 1. So this cancels, right? Because x minus x is canceled. So now I've got a nice delta x in front, right? So I have delta x times, and then all this stuff in here. So I'll just quickly jot that down for completeness. Dot 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 plus x plus delta x, x minus 2, sorry, xn minus 2. Okay. So what I've done here is I've simplified, well, okay, I use the term simplify. What I've done is I've factored that out. But what's kind of nice now is that I have that delta x here. And that means that I should be able to cancel out that delta x and that delta x. And now I should be able to apply the limit from there, right? So that's kind of the interlude. So again, I can express this numerator as this part right here. I'll jam that in there. There we go. Again, this cancels out. So I'm just left with all the top there. It's not super nice looking, but I'm just copying that out. Okay. So using our limit rules, we know that we can apply this limit to each individual term here. And when we do that, basically using our substitution rule, this is 0, which means that I'm just left with x. This is 0 as well. And this is 0. And so, in the end, what I get is x to the n minus 1 plus, then I get x to the n minus 2 times x plus dot dot dot, you know, we keep working our way down, get to the end here. So this is x plus 0, so that's just x to the n minus 2 times x. Plus x to the n minus 1. Okay. So that was page 2, page 3. So again, so I can just kind of cover that there. So just continuing. So I have x to the n minus 1. I have x to the n minus 2 times x. So using our law of exponents, n minus 2. So that's n minus 2, and then we add the exponents, so plus 1 gives me n minus 1. So x to the n minus 1 plus dot dot dot, working all our way down. Same thing, n minus 2 plus 1, so we have x to the n minus 1 plus x to the n minus 1. Okay, so we have all these, and how many of these do we have? Well, in fact, we'll have n of them. So if you notice in here, we had, when we were doing the difference of squares, we had 2 terms. When we had a difference of cubes, it was 3 terms. If we have a difference of n squared, or sorry, you know what I mean, a binomial to the exponent n, then we'll have n terms. So that means that we have n terms. So we have n of these x to the n minus 1. So it becomes n times x to the n minus 1. I think we proved it then. That's what we wanted to prove. So n times x to the n minus 1. And usually I finish off my proof with some sort of symbol to say that this is the end of the proof before, you know, I write some more stuff. So just to separate it. So proofs are just little arguments, and remember that an argument always has some sort of little trick to it. And the trick for this proof is that we used the kind of general difference of you know, we had a difference of squares, difference of cubes. I'm not sure what I'm going to call these, difference of nths. And by doing that, what we reverted back to what we had done previously in our previous lectures. Let me just pop over here. Which was, again, for calculating the derivative, simplifying it as much as possible so that we could cancel out that delta x, and then letting that delta x go to 0, and then that's how we got our derivative. So again, this was kind of the secret sauce that makes it work. Two, three, okay, perfect. Okay, so that wasn't too bad, right? The proof was, you know, just a little trick, a little bit of algebra that we've basically built up our entire high school careers to do, being able to factor, to simplify, and reduce it down to basically just n x to the n minus 1. Okay. Here's an example. Can we differentiate square root of x? And let's say that it's x for greater than 0. So we can, okay, well, you know, somebody might say, oh, well, that's not following the rule. Okay, well, we can do it using our derivatives, our definition of the derivative. So again, we let f of x equal square root of x. We can take the derivative. And I just write out the derivative, the definition. So I have my difference in my y's, my difference in my x's. Now I'm substituting in my value, so I have x plus delta x being put into that function, the square root of x, minus square root of x, all divided by delta x. Still can't put in the 0 in there. It gives me a denominator of 0. So, oh yes, we return back to some more 103 algebra or high school algebra. What we're going to do is we're going to rationalize the numerator, which means that we're trying to get rid of these radicals up top, the radicals being the square roots. And I know it sounds a bit weird, but by doing so, we can get rid of that square root so that we have a delta x on top. We can cancel that out and with the bottom, and hopefully we can then apply our limit. That delta x goes to 0. So that's the plan. What are we going to do? We go back to essentially another trick. Again, we never, when we have an algebraic expression here, we never fundamentally change the equation. So again, here we just have 1 over 1. So by doing that, I haven't changed it, right? I'm multiplying by 1. 1 times 3 is still 3. 4 times 3, or 4 times 1 is 3. Pi times 1 is still pi. So by doing that, I haven't changed it. So but what we're going to do is multiply. We're going to use a special one. So what we're going to do is we're going to use what's called the radical conjugate, or the conjugate radical. And what that just means is we just take this, and instead of using a minus, we use a plus. I guess that's kind of the secret sauce in this kind of proof, which is we have a radical conjugate. Okay. It's pretty quiet in the chat. Hopefully everyone's following along. If it is, I guess I'm almost becoming a Twitch streamer here. You know, thumbs up, some emoticons. So again, I can expand this out. I have a square root times a square root, so that just becomes just 1, right? So it's just x plus delta x plus square root of x times x plus delta x. Then I have a minus here, so I have a minus square root of x times x plus delta x. And then I have a minus, I have a square root times a square root, which just gives me x. And in the denominator, be very careful because this is a delta x and we're multiplying by all of this. This is all together in one term right here. So okay, so now I can cancel out, I have an x and a minus x, so that cancels. The nice thing about this is I have a square root of x. And this term is the same as this term, but it's negative, so I can cancel out that. And so I'm just left with, up top, I'm not doing a high five, not up top, but you know, in the numerator, there. See, I've rationalized the numerator. So when I can cancel out this top here. So I'm just left with, now when you do cancel that out, it's really, you know, delta x divided by delta x, which is still just 1 over 1, which equals 1. Okay, so essentially still it's just 1 on top. And now we can apply our limit. So letting the delta x go to 0 in this case now, I get x plus 0 plus square root of x. Oh, why bother writing? I'm actually going to do that. Okay. There we go. Square root plus square root, which equals 1 over 2 times the square root of x. So that's my derivative. Okay, but was there, after doing all that, after realizing, but didn't we do something that was, can't we use something? Like, we got all these tools here. We have this tool that we just did, right? That we had this proposition that we just proved with x to the n, and then x to the n minus 1 is our derivative. You know, why can't we use that tool here? Like, why not? Can anyone answer that? Can we use that tool? Or maybe we can't. Can we use our rule that we did? Okay, just a second. So I'm going to actually call this proposition is so important that, and also now that we proved it, this is now a theorem because it's important. We're going to call this the what are we going to call it? Let's call it the power rule. Power. You know, with a lightning bolt. Oops, that looks more like a knife. There we go. More like a lightning bolt. All right. If we follow exponent laws, wouldn't... Ooh, that's cool. Somebody wrote... Okay, so I have some people. These are good. Quick! Take a note. That's okay. Take a letter. Take a note. Okay, so, you know, polling the audience. I have some people saying, yes. Some people are saying that square root of x. I can do it as like that. One person wrote, if we follow exponent laws, wouldn't f prime? Somebody's, so this is one person. A second person said, I'm just saying person because I don't know if people are shy or not. So if I, somebody has said, they wrote 1 over 2x to the, I'm going to write exactly what they wrote. So what they've said here is 1 over 2x to the minus 1/2. So I'm not sure if they mean 1/2 x to the minus like that, which then again would be equivalent to 1 like that. But you're on the right track. Again, the idea is that from here we can, yeah, that's what it means. Okay, perfect. Because when I read it initially, I had read that as 1 over 2x to the minus 1/2. And that's what how I had read it, and that would be incorrect, but this is right. Root on the denominator. Some people are more used to it. Some people don't want to see negative exponents, and that's why they may rewrite it. So again, just as a check then, from our example, converting that, we have our square root of x becomes to the 1/2. And using the power rule, yeah, I think so. The commenter was I think he just wrote it like that because there is another rule to change it the way that you and I would have. Yes, exactly. Using our exponent laws. So using our power rule, in this case, our n equals 1/2. So n to the 1/2 minus 1, so there's our n minus 1, multiplied by n, which in this case is 1/2. So we're left with 1/2 x. So 1/2 minus 1, you have an x to the minus 1/2. And then you can neaten that up by putting this into the denominator so we get rid of the negative exponents. So I get x to the 1/2. And sometimes it's neater to write it like that with a square root. So that makes it much faster to do stuff. So we can do many things now. So again, using our rule, I have x to the 6. So again, using our rule, the 6 comes down in front, times x to the, and we drop the exponent by 1. Look how easy this is. Wow, it's amazing. What a feat. We don't have to do all that rigmarole to show something using limits. We can just find the derivative. Which, why are we doing the derivative again? We're looking for the derivative because that's like it's our function. It's the functional equivalent of finding the tangent or trying to find the rate of change. And remember, why are rates of change important? Well, when we were thinking back to COVID, it wasn't enough for me to know how many people were sick or how many people had died. I was more interested in knowing, is the rate of change increasing or decreasing? Are we speeding up the infection or is it slowing down? So we have to always keep this in mind, that we don't get too deep in the forest. Yeah, and we can make much more money. Yes. I can't wait. I definitely cannot wait. Okay. Now the power rule doesn't quite work when we have, well, I said a natural number. So the power rule works for natural numbers. At least how we've proved it works for natural numbers. And this means so it does not include n equals 0. So that's an important case. Then what's the derivative of a constant? So what is the derivative of a constant? And you can put a letter, let's say k or whatever, c. But what is the derivative of a constant? Remember, intuitively, a derivative is a rate of change. So if I asked you, what's the rate of change when something is constant? There is no change. So that is how we can intuitively think about it. So if the derivative is constant, so if I have a function and it's constant, exactly, it should be 0. So I've been using k, which means that there is no change. Which implies that derivative is 0. There is no change, only Zool. All right, ignore that. So that implies that the derivative of a constant should be 0. So that's what we think intuitively. Let's prove it. So here's the proof. So f of x is a constant k. So then using the definition of the derivative, This is probably one of the easier proofs. And the reason for that is because I put that in there. F of x plus delta x. I put that into this function. I still get k. It's still a constant, right? Because there's no change. So that is still k. And then the function f at x is still k divided by delta x. Okay, so you might be worried that, you know, I don't have a delta x now to cancel that with. But we don't have to worry too much, because what we can do is we can simplify the numerator up here. K minus k, that's 0. And you'd be like, wowee, I still can't apply. Yes, but I have 0 divided by something, so that's still 0. And the limit of a constant is still 0. Or the limit of a constant is a constant, and in this case that constant is 0, so that's equal to 0. Perfect. That's it. Okay. So we were able to do functions like the square root, and we were able to do functions where, oh yeah, we went right back to, so we have x squared, x cubed, x to the 4th. Okay, but what about some sort of number? Like if we have what about some sort of function like 3x squared? Well, we can't really apply our rules. It doesn't say anything to do with that. But, it'd be nice, though, if we could come up with some sort of rule. And so this is what we can do for our proposition. What it would be nice to do is, for our proposition, it'd be nice if we can just treat that like a constant, like this, and then multiply it by the derivative. And so what would be nice, we have a rule for that. So it's 3, so we have taking the derivative of x squared, we know is just x. It's 2, so it would be nice if it was 6x. So that's what we're going to kind of show, that if I have a function that's made up by c times a function like that, wouldn't that be like the product rule with limits? Yeah, you could think of it like that, because 3 is a constant. Yep. It'd be nice if it worked like that, wouldn't it? And I'll okay, fine, I'll tell you, yes, it does work like that. It does. I can do that. And that's exactly what I'm going to show you. That if I have this function that's made up of a number c, or, sorry, I've been using k in these lecture notes, so I'll use k. Then the derivative of that, it'd be nice if it was k times the derivative. Okay. So that's what we would like, and in fact it does. I'm saying it's a proposition because I haven't proven it yet, but it is. And this is what we call, we'll call it the constant multiple rule. So by our proof, we have g of x, g primed. And again, writing out our definition. Now in this case, it's g, not f, because that's what we're starting with. Now substituting our x plus delta x into the g. So substituting that in, I would get k times f, and then inside of my x is my x plus delta x minus, and then g is just minus k f at x. Okay, so part of this, the trick for this proof is that we need to get this f prime of x. We need to get it back to this. We would like to get that, because once we get it simplified down so that the limit of delta x goes to 0, we have f x plus delta x and all that, then that's equivalent to the derivative of f at x, or sorry, f prime at x. So we see it here, we kind of see it here, but we have k's in front. So the idea is pull those k's out. We can factor that out. Okay. And in fact, just to make this a little bit more clear, I'll write k times, and now I have this. And as Maple has already mentioned in the chat, I have a product here. So by the product rule of the limits, I have k times the limit as delta x goes to 0 So again, this is by the product rule of limits, which we covered in the last assignments in a couple of other of the lectures, and I think there's a couple, some of you might have gotten a question about that on the quiz. So the limit as delta x goes to 0 of k is just k. And this should look recognizable. That is the definition for the derivative of f at x. And that's it. There's the proof. So in a couple of lines, you were able to show that. It's not that difficult. Again, the trick in this was, I don't know, maybe I'll put it in red. The trick was factor out k or the constant. And then to group terms to get definition of the derivative. Okay. So there's our constant multiple rule. That's kind of, put a box around that because we've proven it now. Now it's not a proposition anymore, it's a theorem. Perfect. So let's do an application of that. So let me just write that out up here. Oops, of course. F. Okay, so, here's some examples. So like, here's A. So now I can do 3x to the 6. If I take the derivative of that, I leave the 3 alone. And then I'm going to multiply it by the derivative of x to the 6. So the 6 comes down in front, x to the 5th. 3 times 6 is 18. Let's do pi, and then we'll do x to the 3. It's getting close to dinner time, so I'm hungry. So I'm thinking of pi. Okay, and then we leave the constant alone. We're going to multiply by the derivative, and that derivative is the 3 comes down in front, x to the 3 minus 1, so that's 2. So some people would prefer to see it as 3 pi x squared, like that. Let's do g of x. Let's do, I don't know, 4 pi to the 7th. And what's the derivative of this? What do you guys think in the chat? What's the derivative of 4 pi to the 7th? Gives me a chance to drink some, catch my voice with some water. So what do you think? 28 pi to the 6th. Okay, I have another person who's saying 28 pi to the 6th. Okay, another person. Okay. So let's do this. I have 4 times, I'm going to do the derivative of this function. But what is the derivative of pi? The derivative of pi is 0. And again, if I take pi and I cube it, square it, or put it to the 7th, it's still equal to 0. Because again, it's a constant. I can't remember. Okay, well, like 3 to the 7th. What am I thinking of? Like, it's a pretty big number though. But I don't have to think about it too hard because I need to just do the derivative of that, and that's just 0. So, oh, 0. There we go. Perfect. Yes, there was no x. So just be careful of that and read the question carefully. Sometimes people apply the rule so quickly that they realize that they see this pi as a variable and it's not. It's a constant for us. Same thing with e, square root of 2. You know, these might not be, numbers that are common for us to see in daily life, but they're still numbers nonetheless, which means that they're constants, which means that the derivative of that is 0. If I did say h, and I did 4 pi and then x to the 7th, then I can start to do the same thing. Again, 4 pi, I can treat that like a constant. So there's the constant out front times the derivative of that, which would then be 7x to the 6th. 7 times 4 is 28, so 28 pi x to the 6th. Okay. So it would be nice. We can do this, we can do that. So that's the end of my example. But what about if I had a function like this, which was 3x to the 6th plus, and I take this one right here, pi x to the 3. Do we have rules for that? The answer is yes. And the answer is in the form of, let's do a theorem or a proposition. And it's the sum rule. So the sum rule is that if I have two functions and I want to take the derivative of them, that it's just equal to the individual, like the inside functions themselves, the derivatives of the inside. So in this case, it would be nice using this rule that if I take the derivative of that, well, I've already solved them, so I have 18x to the 5th plus 3 pi x squared. So that's the rule. We could also look at it as like in a different notation using Leibniz's notation. kind of a d by dx, so taking the derivative with respect to x, that it's just it being applied to each one. Or equivalently, some people will write it like this. And let's prove it. So that's what we're going to prove. We're going to prove that the derivative of the sum is equal to the sum of the derivatives. Okay. So what we're going to do is our proof. So we're going to let h be our, the sum of the two functions. So we will show that h prime of x is equal to f prime of x plus g prime of x. That's what we want to show. So using the definition of the derivative, we have hx plus delta x minus h go. So this is our original function that we have. I have to keep remembering this. That's what we want. And then when we substitute in, we plug in that x plus delta x in that. That's equal to substituting in that x plus delta x into here. I get it. F at x plus delta x plus g of x plus delta x. So I can replace this one up here with this. Okay, minus, and then I substitute in what my h of x is. So I'm just going to put some brackets in here. So I'm going to replace that. So it's f of x plus g of x divided by delta x. Okay, so now that we've got that, the trick is we want to arrange it so that we get the definitions of f prime of x and g prime of x. And we can kind of see them. We see a pair here. We have the x plus delta x. We also have it right here because we'll have to distribute that negative sign here. So let's do that. So just distributing this minus sign to each of them. And now I'm going to start to group them, because I kind of want this one and this one here to be together. And I want this and this here. Okay, so the other thing too is if you have, just as an aside, if you have 3 plus 4 divided by something like 2, that's equivalent to writing 3 halves plus 4 halves, right? So what I've done is I've written the denominator with each of the terms in the numerator. And the same thing here. I can do the same thing. I can group them however I want. So now what I can do, again, I'm trying to get it to look more like what I know, which is the definition of the derivative. So in this case, it's definition of the derivative for f. And then I have plus. Now when I start to break this up, I'm going to, put some brackets around it, because I still want to show that the limit is being applied to all of this. And by the sum rule, of limits, I can apply this to this one and this one. Plus and what's great about that is now you see here's the definition of f prime at x plus. Okay, but that's not how I usually, but this is still the derivative then for finding the derivative of g using the definition as well. So we're done. So what we have shown then is that if I have a function, that taking the derivative of the sum of functions is equal to the derivative of each function. And that's the end of that proof. This one was not too, I guess maybe the trick for this one was just that maybe grouping terms so that you got the definition of f prime and g prime. So maybe that was kind of the kernel of the proof. So maybe as an exercise, if you really want to understand that, just following this outline of the proof, given that h of x equals f of x minus g of x, show that the derivative is f prime minus g prime. But it would follow a very, very similar approach. Okay. There's a couple of things I miss about the chalkboard. I mean, sure, it was messy, but at least you could move around. Sitting in a chair for 2 hours is quite a while. Hopefully it's not too boring for you guys. That if you're interesting little tidbit, half of the people who've watched this are on their mobile phone. So that is, I don't know what, I think that's interesting. Take calculus with you on the go. Differentiate. Did I spell this correctly? Yes. Half are at a computer. I'm stuck to a computer. Interestingly enough, I found out that if there's over 1,000 subscribers, that you can start live streaming from your phone, which I think that would be a dangerous tool in my hands. Okay, so we can differentiate like x squared plus x cubed, which is kind of banal, but just to show this off, again, this is applied to each of the individual terms. So the derivative of x squared is just 2x plus the derivative of x cubed. So what did we do here? This was by the, here's the sum rule, and here is the power rule. Somebody wrote 3x squared. Did I do something wrong? Mr. Walker has written 3x squared. Yep. Oh, okay. I should ask more questions. Right. So the question should I ask is, the sum rule works for two functions. Right? The question maybe I should ask is, does it work for three functions? You know, if I had a function f plus g plus h, does it work for three functions? I'll just let the chat, without offering proof. Yes, it should. Yes, of course. I'm always interested about proofs. Yes. And of course, if you've seen calculus before, or you've seen it, you know, in high school, some people might be able to tell me yes. Okay. How will I show this? Without having to do extra work. That's, or what I have already. That is always what we do in math, is we're trying to squeeze every drop that we can out of the work that we've already done. So if you let me have the sum rule, what I can do here is I am going to do this. F plus G plus H. So what I've done is I've grouped with brackets F plus G. So I'm treating this like one function plus H. So then I can apply the sum rule to that. So that means that I can do F plus G prime plus H prime. And that's sweet by the sum rule. Yeah, exactly. So what you're doing is just a repetitive application of the rule. So again, then I can apply the sum rule again on the inside of these brackets here. So I get F prime plus G prime plus H prime by the sum rule. So then that proves for three rules, or for three functions. So here's my proof. For one function plus two function plus dot 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 all the way up to fn functions, that's equal to f1 prime plus f2 prime plus dot 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 all the way up to fn by n applications of the sum rule. Okay. And for those of you who are going, I don't care about the math. Why are you showing me the workings? Well, that means then I should be allowed to differentiate something like this. Differentiate something ridiculous like this, like 7 times x to the 4th plus 2x to the 3rd plus 5x squared plus 6x plus good old pi. So if we differentiate that, I have 7, that's my constant, and I bring the 4 down in front, x, drop it down by 1 for the exponent, plus 2 times 3x squared plus 5 times 2x plus 6 plus 0. And just simplifying it, 7 times 4 is 28x cubed plus 6x squared plus 10x plus 6. Which is pretty awesome. It means that that would be very hard to do if we were just using the definition of the derivative. But what we've done is we've built it up so that from the past 2 hours, what we've done is we've gone from digging in the dirt with the definition from x to the 4th, which, can you imagine if we had to do that for this long, to do that derivative? We found a pattern and we came up with a rule for this handling the powers, which led us to the power rule, this one right here. We realized that that power rule is also important because we can handle the square root as well by simply rewriting it as a power. Okay, we also realized that the derivative of a constant is really asking, what's the rate of change of constant? Well, it's 0. There's no change. So with that, we just kept building it up. We proved that this is one of the most obvious proofs, which is that the rate of change of a constant is 0. Good. Good to see that the proof works out. And then as well, we went through the constant multiple rule. And we just kept building it up. And then we kind of have you can think of it as an algebra. We can build up the function that we're going to differentiate more complex by having 2 functions that are going to be added together, and then we take the derivative. And we put it all together, and ultimately, after doing 8 pages of math, we can confidently do this in almost 2 lines here. Like, if you get better at this, sometimes people will even skip doing this step here and can write directly to this, so that they end up going 7 times 4, 28, x to the 3rd. So, but that takes some practice. Okay, we're now at 5:30. I will post the notes on Moodle, and also will have assignment 3 available soon. If there are any comments or questions, or you didn't want to post the questions in the chat tonight, feel free to send me an email. You have my email address. It's richard.kohar@rmc.ca. And thank you all for tuning in and for participating in the chat. And I will see you all on Thursday. Have a good night.